Good afternoon, this is Schweitzer. We're going to look through a trend here on atomic radius and looking at, so what are periodic trends? What do they mean? Well, first of all, let's sort of identify what the word periodic means, periodic trends. You'll see that the rows are called, the columns are called families or columns or groups. They have similar properties, chemical properties, but the rows are called periods. And that might be a curious word. The word period really in physics means time for a cycle to repeat. So really period is something that repeats itself, like something happens periodically, you know. But in physics, it's an actual unit of time that for something to repeat. So we're saying that in the period, there's some trends that repeat themselves over and over again. So these trends that we will look at, and there are more than this, but atomic radius and ionization are the two that we're kind of looking at. Okay. Now, what is atomic radius? Really, it's the size of the nucleus. Um, so from the nucleus, size of the atom, from the nucleus to its outermost electron. So it's that distance is radius, but really, it's just telling us the size of the atom. Size of the atom. So there are others, obviously, but okay, well, why do we study these? Well, for our purposes right here, the reason why we study them is because um, it's really just a means of understanding how protons and electrons affect the atom, and allows us to test whether you understand models of electrons, um, protons, electrons, and our modeling of atoms. But there are also lots of implications in bonding, which we'll see in the next chapter. And as you move on and on, the size of the atoms really matter in organic chemistry, as far as why one reaction happens or another one doesn't happen, and how vigorously they happen. So there's lots of stuff involving sizes of atoms. All right, so here we go. First off, why do atoms get bigger as they go down the periodic table? All right, so for this example, we might just draw it all, a Bohr diagram. Um, Oxygen, for example, is right here, and sulfur is located here. So you can see that's bigger, but why? And it turns out that, as people eventually figure out, that the rows of the periodic table are representing number of energy shells. So this guy's got 2 energy electron shells, and this guy's got 3. Okay, so it really has to do with the number of energy levels. Okay, number of energy levels. So this guy here only has 2 energy levels, where this guy has 3 energy levels. So therefore, this guy is bigger. That's really all it comes down to. So moving along here, another example. Now this is a slightly different example. Okay, potassium versus potassium with a positive 1 charge. Here's potassium located right here. But what about potassium plus? Is it still there? Well, this guy's got 4 energy levels. So potassium would be 1, 2, 3, and then 4 energy levels, but it's only got 1 valence electron on the outside. So when it loses that electron, it loses an entire energy level. So now it's isoelectric with argon, and that's something that's kind of important. So we don't really want to compare potassium to potassium plus. We want to compare potassium to argon. And this situation where it only has 1, 2, 3 energy levels. So this guy is considerably bigger, not even close. Okay, look at potassium, look at argon. Okay, big difference. So those are 2 kind of scenarios that we would choose from to pick questions for things of this nature. Simply rows, or if an atom loses electrons and bumps back. So calcium could lose 1 electron, so calcium's got 2 valence electrons. Losing 1 wouldn't make it all that small, much smaller, but losing 2 of them would bring it way back. Okay, so next up, determine which one's larger. Okay, so the first thing we do is just find them on the periodic table. lithium is located right here, and sodium is located right here. So therefore, sodium is bigger. This guy has 2 energy levels. This guy has 3. Na plus. Okay, this guy here we just mentioned has 3 energy levels. This guy only has 2. Its isoelectric width back here. Well, who's that guy? Let's go check up periodic table quick. Yeah, the argon or the sodium bumped back to neon. Okay, so neon is what this guy is. And this guy is bigger. Not even a little bigger, a lot bigger. Okay, you could draw some board diagrams of these things. Let's say, for example, the lithium. Lithium would be, you can see this more visually, 2 energy levels. 1, 2, 3 electrons. Okay, sodium has 1, 2, 3 energy levels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. Na plus would lose this electron, just exposing this inner ring. And therefore would just be like this. And it's not, I say it's isoelectric with neon, but it's not neon. The protons determine the element. It's just electrons are in a stable configuration, just like neon. Okay, and let's move along here. All right, so why do atoms get bigger as they move down the row? Okay, let's compare, let's say, neon and oxygen, so, or nitrogen and oxygen. So if we drew out some of these guys, and we will here in a moment, let's skip to the next page. We'll come back to this one. You'll see it in your own workbook there. So let's draw a picture of this once. We got nitrogen and we have oxygen. This guy's got 7 protons. This guy's got 8 protons. They both have the same number of energy levels. Okay, 2. So you might say that, well, they're very similar size. And they are very similar size. So that's one thing to kind of keep in mind. 1, 2, 3, 4, 5, 6, 7 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay. So what's going on here? First of all, they are very similar in size. Okay. But there's something going on. It's saying here that why are atoms getting smaller as you go to the right or larger as you go to the left? It's a pretty general trend. Now there are some exceptions throughout here. In fact, nitrogen oxygen might be an exception. But in this situation, what's going on here? We have this thing called Coulomb's law. And it's probably the most fundamental law of chemistry. It says basically that, in a nutshell, positives and negatives attract. Okay? And in that case, 2 positives repel, 2 negatives repel. But the math on this thing is the force of attraction or repulsion is the charge of the positive times the charge of the negative divided by the distance squared. That squaring there really is a big deal. Okay? So in this situation, our distance is governed by the nucleus as it reaches out to an electron. Okay? And that distance there is relatively similar to the distance here. Okay? Because we have 2 electrons each. You'll notice that in the previous example, we were just looking at the size, the number of energy levels, because that really determines the distance. So in this situation, you should note that in a nucleus, that as we increase our protons, or our electrons for that matter, what happens? We have an electron here. All it does is it sees this nucleus, and it's attracted to it. That's Coulomb's law. This is the charge on the proton. This is the charge on an electron. This is always an electron charge. This is always the nucleus charge. So if I add another proton, this guy is attracted to greater. But so would electron on this side, attracted to greater, right? I could add another electron here. This guy doesn't, this guy isn't more attracted. So with that being said, as I add protons, my attraction gets bigger and bigger and bigger. So I start getting a slightly smaller. We call this idea effective nuclear charge. Okay? These two atoms here are good examples of effective nuclear charge. What we're saying here is we're adding to the same energy level. So the distance is the same. We're simply adding more nuclear matter. Therefore, this goes up. That's effective nuclear charge. If we're increasing an energy level, well, that would not be an example of effective nuclear charge because we would have a massive distance change and therefore the force would drop drastically. Either way, so this is an example of effective nuclear charge, and therefore the increased number of protons causes this atom to be ever so slightly smaller. Okay, and that is why, as a general trend, we get slightly smaller as we go to the right or bigger to the left. Is because there is essentially, okay, there's more protons, and now we have this idea that it increases, right, Coulombic attraction. Okay, and that's how you'd want to kind of explain that. All right, now nitrogen versus oxygen. Once again, this guy is slightly smaller because of the fact that it's got increased number of protons. Aluminum versus argon. Okay, aluminum's located here, argon's located here, and argon is slightly smaller. Now it's not a ton. Why? Increased number of protons, and therefore increased Coulombic attraction. These are examples of effective nuclear charge. Do you need to memorize this name? No. No, you don't need to memorize that name. You know, if you don't ever want to use the term effective nuclear charge, perfect. If you don't want to use that, then you got to describe force equals charge, like that. And I often tell people in advanced chemistry, like, okay, if you don't fully understand this term, then do not use it. Just talk about Coulomb's law and talk about energy levels. That's all you got to do. Okay, say, oh, we got more protons, it pulls in a little tighter, so it's smaller. That's it. Okay. All right, so on this one, we've talked about effective nuclear charge. We drew some Bohr diagrams out. What's Coulomb's law? Great. All right, so did you know that fluoride is bigger than fluorine? This one is bigger than that one. Not a ton, just a little bit bigger. So the question might be why? This is fluorine, this is fluoride. All right, so what happens here is that, well, this is negative, and it's attracted to this nucleus, pulled in, and the question sometimes has been asked for, gosh, thousands of years, why don't the electrons crash into the nucleus? I mean, they're negative, right? And they're attracted. So they're not moving, so therefore, whatever force is pulling in has to be balanced by kind of an equal force pushing out. Well, what's that force? Well, it turns out that Coulomb's law does have a repulsive force. Charge of a negative times the charge of a negative divided by the distance squared. So this is a repulsive force. Okay. Repulsive force right there. All right, so what happens is as they get closer and closer together, they start to push away from each other. And that eventually pushes them out. And that is the outward force. So that just happens to be that when I add an additional electron here, so it's the same process happens. They don't like each other. They push away, and that ends up pushing it out ever so slightly. Unless, of course, when you add an electron, it fills it entirely, causing you to build a whole new energy level. Then, okay, that's a big jump. That's not necessarily Coulomb's law. That's not necessarily repulsion of electrons. It's understanding the modeling of electrons and how they add in. So, if we're just adding electrons, we always get bigger. Okay? But is it getting bigger because they repel each other slightly, or is it getting bigger because they're adding an entire energy level on? You need to decide. One's a slight increase, one's a big increase. All right. So, is this just Coulomb's law? Well, the answer is yes, maybe. All right. Again, you need to decide, am I just Am I just adding electrons on so they slightly repel out a little bit, making them slightly bigger? Or am I adding an entire energy level on, making it a lot bigger? Okay. So these examples we typically are ones involving negative ions. We can't typically just do examples like this with positive ions because why would this not work? So for example, we're looking at oxygen versus oxide. Okay, they both have 2 energy levels, and this guy's got 2 valence electrons. So I shouldn't say that. It's got 6 valence electrons, missing 2. So as I add my 2 electrons in, I keep the same energy level. This guy is slightly bigger because of electron repulsion. Okay. This guy, lithium, the metal's a little bit different. They're losing electrons. So this lithium's got 2 energy levels, and it's going to lose this entire guy. So this whole electron repulsion thing really only applies with the non-metals because the metals end up losing entire energy levels, which of course then causes a very drastic change. Okay. Okay, draw a Lewis structure. Got a couple of those Bohr diagrams. There we go. All right. So, problem solving methodology. And we'll try this out here. Okay, this is the general pathway that we use to sort of dissect and investigate things. All of this has to do with 2 things. One is Coulomb's law. Force equals the charge times charge divided by distance squared. And the other is the idea generally of Bohr diagrams and how electrons fill in around atoms. Number of electrons and energy levels. Those 2 things together, you have everything figured out. So the first thing we look at here is find the rows the elements are in. So let's say sodium versus sodium ion, okay? So sodium, let's find here, sodium is located right here, and therefore it's right here, okay, and the anion is right here. So that's actually neon. It looks like neon at least. So we find them in the energy level around here, okay? So in this case, just simply look at energy levels. Therefore, Na is considered to be bigger than Na+. Why? Energy levels. And I'm giving a blurb statement here, but you could write a complete sentence to make this clearer that Na has 3 energy levels, Na+ only has 2. Therefore, Na is larger. Alright, so the first thing we do is really just look at the rows the elements are in. This tells us the number of energy levels, which is a huge factor. Alright, what if they're in the same row? Well then, they're similar size. And now we need to look at number of protons. This is our idea of effective nuclear charge. Yeah, I'll show you effective nuclear charge there. So that's going to be an example of nitrogen and neon. Nitrogen is located here, neon is located right here. So they both have 2 energy levels, they're of similar size. But neon's got more protons, so it's slightly smaller. So there's more Coulombic attraction, given Coulombic. And that's really what we'd want to say. Neon has more same number of energy levels, but more protons, so it's slightly smaller due to increased attraction, pulling the electrons in slightly a bit. So keep this idea in mind. Now, just on this one and this one, if they're all the same, the last thing we'd have would be going to number of electrons, which we did right here, showing that electrons, one more yet, the same idea there, that electrons repel. So these guys have the same energy level. They have the same number of protons, but different electrons. Electrons tend to make things bigger. Okay, so electrons repel, or electrons more energy levels. You got to decide on that. That might get, if it's energy levels, then it should be handled in the first row example. All right, so let's try a couple examples here. Okay, first thing you want to do is just find your atoms. I got lithium located here, and you should be pausing these videos and be able to try it out. This guy is isoelectric with helium, which is located right here. Therefore, this guy is bigger because of energy levels, reason number 1 off our last chart. Lithium versus beryllium. Lithium's here, beryllium's here. This guy is slightly bigger because of Coulomb attraction, reason number 2. And then lithium and helium, okay? This guy is considerably larger. Lithium, helium's here because of reason number 1, which is energy levels. A lot bigger. Lithium plus versus helium. Okay, so now lithium plus is helium. Its electrons look like helium, isoelectric. So now they're both at this spot, but lithium has more protons, so this one's going to be slightly smaller because of more Coulomb attraction, reason number 2. All right, and then boron's located here, but it's not boron, it's boron plus 3, so it's back to helium versus helium. Once again, this guy's smaller because it's got more protons, reason number 2. Okay, you could also compare these two now. You know, boron plus 3 and lithium plus 1. They're both isoelectric with helium. So they both have the same number of electrons, which is 2. But this guy's got more protons, so it's smaller. Okay, nitrogen versus nitride, so they're both nitrogen, but the nitride is isoelectric with neon. So this guy has 10 electrons, so it's neon. And therefore, due to electron repulsion, this guy is slightly bigger. All right, and that is probably going to be the end of our trend of atomic radius. Thank you.